I think we'll start. I want to thank everybody for coming. So today we're going to be talking about a lot of the work that we've been doing in the health and social environments at DARE. So DARE was originally funded as a ARC centre in resources and analytics, but a lot of our work that we've been doing has also spilt over into the health and social environments. And just like the natural resources, the focus is always on how do we think about models, how do we evaluate uncertainty, because that's really important. If you make decisions, you need to understand the risks inherent in the decisions that you're making. And so I'd like to use this opportunity to talk to you about the work that we're doing in the health and social environments. So I'm going to start off with an overview, and then I'm going to introduce some of the fantastic people that are working here. I'm really just so very lucky and blessed to have such great colleagues. Vincent is going to be talking about a paper he wrote in around the COVID and New York. Andy has been doing some excellent work around COVID model averaging, as well as doing some interesting work around childhood obesity and the factors that predict childhood obesity. And Roman's going to sum up. Roman is our senior research fellow in this area, and Roman has been doing a lot of work pretty much on most of the stuff that everybody's been doing, in addition to things like the lockout laws and policing and domestic violence. So we're trying to give you a sense of the range of social issues that we are applying these techniques to. So without any further ado, let me just go on to the talk. So last year, Roman and I wrote a paper. This appeared in the conversation, and it was around the lockout laws. And the reason I've got it up here today, it's just because in the conclusion, we came to the conclusion that basically acknowledging uncertainty is fundamentally important, particularly if you're going to infer very complex quantities, such as a reduction in violence, from data. So that's a very complex phenomenon. What makes people violent? Under what conditions are they violent? What can we do to hinder it? There's always going to be a lot of uncertainty with inferring those complex quantities. We use models to try and understand things, but we all know that all models are wrong, just some are really useful. And so we're going to be talking about attaching probabilities to models, and also trying to think about ways in which we can compare models to see which model might be better than another one. So that's the first reason, is that if you don't acknowledge uncertainty, I think what happens is the public lose faith in models, because they say, oh, well, they said that this was going to happen and it hasn't, or vice, or something along those lines. So we need to do it to build trust with the population. And the second thing is because we want to have a good outcome. I mean, we should never accept that we know things. We should always strive to look for other possible explanations. If we don't, then we concluded in this article that we may fail to achieve an outcome that everybody wants. So this was around the lockout laws. I'm sure everybody, all the people involved, want a reduction in violence and a healthy nighttime economy. That's what everybody wants. The question is, how do we get there? And if you focus on one thing as the explanation for any reduction in violence, you actually may be misattributing a reduction in violence to that one thing. And it's actually not going to be optimal because maybe there were other things going on in the background. And that's particularly also true of COVID-19. So we're going to be talking about those sorts of things as we go through. So keep those in mind. One, we want to build trust with the public. And two, we never want to stop looking for and searching for alternative possible explanations. So when we're talking about models and uncertainty, it's useful to categorize models in one of two ways, although they are very much related. So predictive models. A predictive model is one that says, well, what's the probability distribution of possible the number of COVID cases that Victoria is going to report tomorrow? We might say, well, you know, hopefully it's going to be less than 100, maybe an average of around 80, and it could be anywhere between, you know, 50 and 90. That would be a predictive model around what the number of cases in Victoria is tomorrow. We don't really care if prediction is the only thing that we want. We're not really concerned with inference. Then that's as often a different class of models we build than if we are actually interested in making inference. So what do I mean by inference? I might want to say, well, you know, I have an intervention, which is lockdown in Victoria, And what was the impact of lockdown on, I'm sure everybody's heard of the effective reproduction rate. If you haven't, you will hear about it a lot this afternoon. It's the rate at which, if one person gets COVID-19, how many people do they pass it on to? And so typically what we use to denote the, an unknown, a parameter, which in this case would be the impact of lockdown, we give it a Greek letter. I don't know why that has grown up as a sort of norm, a Greek letter for a parameter, but when we're actually predicting outcomes, we tend to give them a letter from the Roman alphabet. So that's just a piece. So what I'm going to be doing today initially is talking about inferential models. Okay, so I'm going to be talking about it with two examples. One, which was a paper that we did about 18 months to 2 years ago, which are the factors which lead to youth disengagement. And the second one is going to be, example is going to be about what is the impact of various non-pharmaceutical interventions. So for example, social distancing, lockout laws on COVID-19 transmission in Europe. This was a paper that was focused on European countries that we wrote. Okay, so we're always Bayesian, which means that what we do is we say, given we've observed some data, how likely is it that this model that I've proposed is the correct model? Now, I will explain this slide in a little while, but just to take you back to those of you who've done some work in statistics, you would normally do this by, say we had an outcome. In this case, it's predicting whether or not somebody is going to end up not in employment, education or training. That's called being neat. If they're not in employment, education or training for 3 years, the chances that they ever get out of that category are less than 1% for the rest of their life. So this is a big problem, not just for the individual, but for society as a whole. So we would like to be able to understand what factors are predictive or what we can do to intervene in order to reduce the probability that an individual is going to end up in that category. Now, we have lots of factors on individuals available that we can use to be able to predict it. So those factors, if you look at that thing that looks like a scanner, a bar scanner, it's not, it's a map of models and factors, and I'll explain it. Along the bottom axis, the x-axis, we've got factors. So there might be things like the location where the person lives, their age, whether they're male or female, level of education, if they've got a criminal record, how much alcohol, how much cannabis, what's their sleep patterns like. So we've got a range of factors that are available to us to build a model. And what we want to know, the million-dollar question is, what is the combination of factors that best predicts it? Now, if you are normally doing some sort of multinomial logistic regression, that may be one way that you might do it if you've done a little bit of stats at uni. You have a model that says, I'm going to put all these things into my logistic regression and I'm going to use some criteria, whether it's some stepwise criteria, whether it's an information criteria, about which model that you select. And the key is there that you select one model, right? You say that this is the model, you've got p-values that are all less than 0.05 or something like that, and you say, so this is the best model. That's in a Bayesian framework, it's a very different way. We don't actually put we don't ever see p-values. What we do is we try to select which models are the most probable. So a model here is defined as a collection of factors. So if you've got 5 possible factors, you've got 2 to the 5, which is 32 possible models. If you've got 50 factors, you've got 2 to the 50 possible models. So 2 to the 50 is more ants on, is the number of ants on Earth. So there is no computer that's going to be able to do, compute the model probability for each model if you've got a large number of factors. So we have to come up with algorithms that try and explore the model space in some sort of effective manner. There's the model that we develop at the center. We start out with the maths. We write down what we want to do. We write down what the posterior distribution of a model is, like how probable is that model given the data. And then we have to, depending on the complexity of the problem, program up what's called an MCMC scheme in order to search that space. It's quite technical and it's often really hard to do. And Andy is going to be talking about network models, which are even harder because the model space is just so much larger. So what I want to do is just take you through what that graph looks like. On the y-axis, there's models. So these are the top 100 models out of the top 2 to the 50, out of the possible 2 to the 50 models. So each row is a model. So if you run your eye along the top row, that is like model 1, every time you see a dark bit, that variable that's on the x-axis was in that model. So the first one had the center, so the location of the person, the age of the person, whether the person was male or female, and you run your eye along and you can see various bits and pieces, or you probably can't because the writing is very small, but I can tell you now depression is in there, I think maybe even criminality. I've got them listed on another slide. The point of this graph is to say that if you see a black column, that means that that variable is in every one of those 100 models. And for each one of those models, we are computing the probability that it is the correct model. And when we go to make a prediction, we're making a prediction averaging over all possible models, where the average is with respect to its posterior distribution. And we can show not only via mathematics, but also via simulation, that you get much better predictions, much more accurate predictions if you do this than if you just select one model. So this is the idea, is to how do you attach uncertainty to models, and this is the way that we do it. So what did we find here? The trouble, so this is where it becomes very difficult if you're a policy person and you have to intervene, because it's not so clear what is the best model. If we look at the most probable model, that is the one that was on the top, that has education, depression, sleep, and emotional abuse in it. So they're the most probable combination of factors. If I look at one with the highest predictive ability, and again, for those of you who've done some of this, this would be represented by the area under the curve, under the ROC curve, you would get a different set of variables. So there's some overlap, but you can see you've got a maternal authority if you're a bossy mum. I always look at that and think, oh my God, I hope I wasn't too bossy. Emotional abuse, physical neglect, and fatigue. Both models, but even though the other one has a slightly higher predictive ability, they're comparable. And of course, this represents a problem, because if you're a policymaker, it's all very well as a statistician to produce you with all these models and probabilities, but the question for a policymaker is which intervention strategy should you use when you are really unsure about what sort of variables might impact whether somebody ends up in that neat category, which is what we want to avoid. So I want to sort of answer that question a bit by looking at this graph that you see now on your left. What you see on this graph on the x-axis is our prior probability that a factor is important. So we might say we're confident that the gender of the person is important, or the age of the person is important. And that's a probability that we are free to choose. That's obviously going to lie somewhere between 0 and 1. The probability that that factor is important is something that has to lie between 0 and 1. And then we observe some data, and that's what the y-axis is. So the x-axis is probability that the variable is important prior to seeing the data, and the y-axis is the probability that the variable is important given the data. So what does this tell us about? This doesn't actually tell us which is the best model, but what it tells us is where we need to focus our attention on. So there are basically 3 clusters of factors. Those ones at the top, age, depression, and the sex of the person, are clearly in the model pretty much independently of what I believe a priori. So here, this is 0.01 down here, and you can see, if I even put a 0.05 probability on them being important, by the time it gets to 0.1, I'm really sure that these variables are important. So in other words, I'm quite confident about this. On the other hand, we've got a second set of factors, which are here. And here we're pretty sure that this dotted line, by the way, is a 0.5 probability. These ones, we're pretty sure they're not important, right? So we have to get prior probabilities of believing that they're important over 80% or over really 90% in order to believe given the data, that it's a 50-50 chance that they're in or not. So these ones here, we're quite sure are not in. So these ones are in, these ones are not in. And of course, these ones are the ones that we're really unsure about. So these are criminal record, lack of friendship groups, and education. So why are we unsure? How do I infer that we're unsure about these given this, given these graphs? It's because you can see that almost as I move my prior probability, my posterior probability is just changing with that. So what we can say is that around this group of variables, the data is not really informative. Everything is being driven by my prior beliefs. And so this then could be used as a motivation for actually studying this further. So this is one of the great things about modeling uncertainty is that it identifies areas where you're not really sure of, and so you can go away and do a bit more research on that. So that was one example of where we're looking at model uncertainty to solve what is a pretty pressing issue in developed countries, which is not in youth disengagement. So I'd like now to quickly turn to a tale of what's called a tale of two models. So this is a paper, or rather a letter that we wrote to Nature around the impact of non-pharmaceutical interventions on the spread of COVID-19. I think I might skip those. These are just models. On what you're seeing on the left-hand side of your screen is models that are used to predict how the COVID-19 spreads. These are from a paper that appeared in Nature in June 2020. Of interest to us is this thing RT, because it is the effective reproduction rate. It's trying to look at how this changes over time and in response to interventions. So on these graphs, what we have here, this is the number of, these are the dates. The pink bars are the actual deaths on dates, and these were the predictions of the model. So this is doing a pretty good job at predicting. This is the Imperial College model. It's doing a pretty good job at predicting the number of deaths. And the way that they modeled, because they had a model for how this effective reproduction rate changes over time, they said it's constant unless there's a non-pharmaceutical intervention. And those interventions were, so the first one in this one, I believe, is self-isolation, and then there was social distancing, which was followed by school closure, and then lockdown and event ban. And you can see this sudden drop in RT, right? So this was their model. They said that it only changes in response to interventions, and they were trying to get at what were the important interventions. And the data went up until May the 4th. They started in March and it went up to May the 4th. Well, this is all very well, but there are many other explanations or many other ways to model that this RT is varying over time. One of the problems with this model, I'm sure you'll appreciate, is that if you say that it can't change unless it changes in response to interventions, you're going to find that it changes in response to interventions, because what we do know is that RT changes over time, okay, particularly as it spreads more throughout the community, but also because behaviour changes. So they also had another model. That's why it's called a tale of two models. Before I go into that, I should just say that they came to the conclusion, which is not surprising looking at that graph, that lockdown was the most important feature in terms of reducing the transmission, and that they estimated lockdown was averted approximately 3 million deaths across Europe as a result. But they also had another model, and this model, they modelled RT in a different way. They modelled RT, this is the model that they used for the US, as a response to mobilities of individuals. I'm not going to go into every detail of the model, but basically they used Google, some data from Google to see how, to model how much people were moving in various areas. So how much were they staying at home? How much were they going outside their home area to a shopping centre? How much to work? And so this is a totally different model of the evolution of RT, because the impact of those pharmaceutical, non-pharmaceutical interventions, that the whole point of them is to reduce mobility. Because that's what stops the spread. Infectious diseases can't spread if you're not in contact with anybody. That's the definition of an infectious disease. But in this model, they're modeling the actual mobility, or the RT in response to mobility directly. So these are, now if you run these two models, the first one is the one that you saw just recently, and the second one is based on this second model. So, and you get a very different picture as to what's really causing the RT to fall. In the second model, if you look along, you can see probably social distancing had a big impact, and then school closures had another impact, and so on and so forth. So if you had to be a betting person with the second one, you would say, sure, lockdown had an impact, but so did everything else, and probably social distancing had quite a substantial one. The interesting thing is, what I want you to do is just have a look at these two, right? So these are entirely different models, and yet they give about the same fit to the data. So they're equally good at explaining the data. So two models, very different takeaways in terms of what you should do for COVID-19 reduction, and yet and equally explaining the data well. So this is going back to what I said before. This is a very difficult problem. Now, I'm just going to go here. So if you run these models out a lot more, so we then ran them out all the way until I think the beginning of July. So here are the models, but now they're going all the way out through July. This is model 1, this is model 2. This is model 1 blown up around that area, and this is model 2 blown up. So this is blown up around this area, so you can see things, and this is model 2. So here, what we can see now that we've got this extra data, you can see that the impact of lockdown in the UK, based on their model, so this is not a model we've come up with, this is the Imperial College model, based on their model, is modest. And the biggest impact was, in fact, social distancing here. You can see that had the biggest impact. And we did this for a variety of countries, and happy to share. It's up on the Medi archive, and there's a link to it if you want to have it. It's short and it's easy to read. 10 out of the 14 countries showed no change in RT in response to lockdown. So these are, and yet again, let's look at this, these fits to the data, very different RTs, approximately the same fits to the data, very different inference. So it is not, and we concluded in the paper by saying, well, I know it's tempting to congratulate ourselves on our decision to lock down, but we should resist the temptation and keep looking for other possible explanations, because failure to do this, and therefore misattribute causation, could mean we fail to find the optimal solution to what is a really challenging and complex problem. This is not to say that one model is better than another, but only they give very different takeaways about what interventions to use. So this is again an argument to start doing some more testing, sort of real-time experiments to try and nail down what are the which model works under, or which intervention works under which conditions, and which countries are more susceptible to one intervention than another, and so on and so forth. So I want to leave that there. This is just sort of to put it out to you about, this is how difficult I think it is to make decisions in the health and social sciences when the data is ambiguous. But at least this is a rigorous way of approaching that ambiguity, of attaching models, and of identifying areas that we need to then narrow down on. I'm going to stop now because I'm going to hand it over to Vincent, who is going to be talking about a paper that he's the lead author on, which just has appeared in the European Journal of Clinical Epidemiology. Okay, I'm going to stop sharing. I think I do this. Vincent, are you okay to share?
Yep. All right, thank you, Sally. So I'm going to present one of our work, which was recently published at the European Journal of Epidemiology, where we look at the performance of different models at predicting the daily number of COVID deaths, as well as the ICU bed usage in the state of New York. Yeah. So I'll start off by showing a graph of the daily death count in New York, which is from May 15 to June 5th, and that is compiled from 5 different sources of data. So now the task of defining the actual ground truth for the number of deaths is somewhat problematic that it first appeared, because as we can see from the graph, the numbers are very different from each other, and it fluctuates significantly, especially in the early day of the pandemic. And while many people will regard the Johns Hopkins Uni data as the gold standard, there actually are two versions of it. So one, which is the GHURD in the red color, so that represents the raw data version, and then the second version is the GHUTS. So that's in blue, and that represents the time series version. And you can see that both versions, they are very different from each other. So for example, the raw data version is the lag version of the time series before the mid of April, and it has a big spike on April 15, where there are over like 3,000 deaths reported. And on the other hand, we have the time series, which shows that there are like more than 100 people resurrected sometime on April 19th. And finally, we have got the New York Times data in green, which appears to be smoother compared to the rest of the other sources. Yeah. So putting aside the issue of data quality, so to see how well the models are predicting daily death, we look at 4 different models. So we have got the IHME model, which was very influential in early decision-making at the highest level of the US government. And we have got the LANL, which has a very successful history of forecasting flu in the US. The next one is University of Texas at Austin. And then finally, we have the YYG, who is an independent researcher. So each of this model, they use like different ground truths. So yeah, as you can see from the video, it's like the black line represent the ground truth used by the different models. And then the color line is the forecast series produced by each model. So here we have a plot which combine all of the forecasts produced by each model. So the forecast series, they are color coded in rainbow color, so that the earliest series is in red color, and then the latest series is in violet. And then the black lines are the ground truth, and then yeah, the ground truth used by each model to train their model. And especially for the UT, because they are using 2 different ground truths, we have got the black line which represent the New York Times series ground truth, and then the gray line which represent the Johns Hopkins Uni Time series data. So each of this model, they update their prediction at different frequencies, and then the length of the forecast series is also different between the models. So to evaluate the model, we first look at the accuracy of point estimate. So that is like how close each of the color line approximate the ground truth in black color. So to calibrate their performance, we compute the maximum absolute percentage error, and also the absolute percentage error average across the entire length of the forecast series. So if you just look at the the first red dot on the second row in the training ground truth column, so the value on the y-axis, it represents the distance in terms of the mean absolute percentage error between the ground truth and the first forecast series, which was produced by the IHME model in the previous spaghetti plot. So as we can see, there's no clear winner, irrespective of the ground truth used for comparison between the different models. And some of these models, they are performing better compared to the others, over different subsets of time frame. Yeah. So we also look at the accuracy of uncertainty quantification, because this model, they also provide the 95% prediction interval. So in the graph on the right-hand side here, so we have the rows for different models, and then the red dots represent the training ground truth used by each model, and then the black dots are the point estimate, and then the vertical bar is the 95% prediction interval. So, and on the columns here, on the columns, we have different number of days ahead prediction. So from 1 to 7. So 1 day ahead prediction means that that's the prediction which is made for tomorrow. Sorry. So 1 day ahead prediction is the prediction for tomorrow, which is made today. And then the 2 days ahead prediction are the prediction for the day after tomorrow, which is made today, and so on and so forth. Yeah. So if you just look at the 1 day ahead prediction for the IHME model on the top left, so the black dots, they are obtained by gathering like the first point in the color spaghetti, like from the IHME model. And then the 2 days ahead means that we take the second point in each of the forecast time series and so on. So for comparison, we also compute the coverage probability of the prediction interval, and also the percentage of prediction that are within 10% of the ground truth. So theoretically, for 95% prediction interval, the ground truth must be inside the prediction interval 95% of the time. Okay. So for the IHME model, we find that there are approximately 54% of the prediction. They are inside the 95% prediction interval for the forecast series made between March 24th to March 31st. And then for the time series made between April 3rd and May 3rd, that increased up to 74%. So this is hardly surprising because the model had a revision on April 2nd. And then in the revised model, the uncertainty limit have been enlarged, as you can see from the plots in the first row. Yeah, and even so, this is still far from the claim 95%. And then on May 4th, the model had another revision, and this time the width of the prediction interval is reduced significantly. So overall, we find that the LANL has the best observed coverage, and if we look at the prediction within the 10% of the training ground truth, which is on the last row, and it seems that there's no model that achieves like more than 30%. So we now turn our attention to the prediction of the ICU bed utilization. So out of the 4 different models presented previously, only the IHMD is producing the forecast for the ICU bed usage. So this plot shows that the ICU bed prediction for March 25th onwards, and the 95% prediction interval is given by the gray shaded region. And then the blue line is the maximum ICU capacity, and the red line is the ground truth. So based on this plot, we can see that the number of ICU beds is obviously over-predicted. And so does that matter? And what we'll see next is that in anticipation of the catastrophe, so this news article by the Associated Press report that over 4,500 COVID patients, they were sent to a nursing home. And nursing home, we know that nursing home are full of vulnerable people, and we know that COVID mortality rate is very high among the elderly. And this has caused close to 6,000 deaths in New York nursing home alone. So here are the subsequent forecasts made by the models. And if we just look at on the third row, so that's like the forecast made in late of April. And you can see that the bed usage is now underestimated, and it's predicted that there'll be no ICU bed required for COVID in the middle of May. So that is clearly isn't the case in reality. So as a conclusion, we find that the prediction interval for the LANL model is the best match for the 95% nominal coverage, and only around 10% of the predictions were within 10% of the training ground truth. Model predictions, they are extremely critical in the early phase of an epidemic for early decision making on resources allocation, where we saw that the wrong expectation can lead to very wrong decision made. So the major takeaway from our analysis are that serious thought and investment should be made in quality data collection when the consequences of policy decision are impacting the life of millions of people. And then the models, they must also need to be subjected to real-time performance tests. So I'll just end the presentation with a quote from the New York governor. So he says that now people can speculate, people can guess. I think next week, I think 2 weeks, I think a month. I'm out of that business because we all failed at that business, right? or the early national expert. Here's my projection model. Here's my projection model. They're all wrong. They're all wrong. Thank you.
Thank you, Vincent. Andy has been working on both COVID-19 and childhood obesity. And so he's going to talk about those pieces of work.
Yeah, can you see my screen?
Yes, we can.
Yeah, thank you. Yeah, I will keep as short as I can due to the time limit. So I will give two projects today. So one is for COVID-19 prediction, and one is for Bayesian network model for childhood obesity. So the motivation of the COVID-19 project is showing here. So this is a figure from US CDC website. So you can see here there are so many models for forecasting the COVID-19 death number, infection, and so on. The CDC just use a simple average of all the available models to get a combined prediction. Just as Vincent just showed that most of the models has largely failed, and also has some other papers show that the models failed in different ways. So the goal of our project is to show, can we just combine these available models, get a better prediction? On this table just shows some summaries of the absolute error, percentage error for part of the models. So you can see the column of mean here. So that means on average there are 30 to 50 absolute percentage error for these models. So we're going to build an ensemble model. So this model is using the linear combination of the available single predictive models output as the covariates in this ensemble model. And this is a linear combination plus some noise. Just for a quick talk example, if we just include GENOVA1, UT1, and YYG1 as the covariates in this ensemble model, so at time 0, we don't have any observation. We have no data, no observation. So we just set all the coefficients of these three models to be 1/3. And when we get one observation, so we just update the coefficients according to this posterior equations. And we can keep updating the coefficients as we can get more and more data. So here shows just 7 data points. So that means we have 7 observations. So you can see the change of the coefficients over time. So we can apply this procedure to the real data. So this is for ensemble model for the whole US death number. So this is ensemble 1 and his ensemble 7. The difference between these two ensemble models is we're using different single models as covariates in this model. So this is behaviors of the coefficients over time. You can see they're getting converged, and also the variance of the coefficients is getting smaller and smaller. That's expected. And here just shows the latest results of the coefficients. So you can see more clearly that they are getting converged. So this table shows the performance of the ensemble model and also the previous mentioned the single models. So this is mean of the absolute percentage error. And on average, you can see the ensemble models are just around 20, but these single models are around 30 to 50. So we can say it reduces the absolute percentage error. And we also need to consider the uncertainty quantification as just as Vincent shows. So this is our predictive posterior distribution of the death number. The white triangle is the ground truth. We can see that the white triangle falls in the box plot. That means it's good because our predictive distribution can cover the ground truth. This table shows more specifically results. So the ensemble models can perform as good as the YYG models here and much better than the UT models. If you look at the UT ensemble models, we're just using UT single models as covariates in this ensemble model. It performs much better than any single UT models. So now we can conclude this. So the ensemble models can reduce absolute percentage error from 30, 50 to around 20. And in terms of the uncertainty quantification, the ensemble models perform no worse than any individual model. And when you look at the UT ensemble models, it shows that even the bad individual models can produce pretty good results by using our ensemble techniques. Yeah, this is the second project, which is on Bayesian network for childhood obesity. The motivation of this work is we know childhood obesity is a serious public health issue. In Australia, 1 in 4 children is affected by overweight. And we know early obesity prevention is beneficial to the future life, but we can't find any systematical study on this. So we are aiming to get to know better about these factors of children's obesity. So we're using the data from longitudinal study of Australian children. So here's the overview of this data set. And here are some variables we are going to build the model. The BMI is children's BMI. The BM1 and the BM2 are the parents' BMI. And the ME1 is mother's education level. And SE is the socioeconomic status of the family. So these variables in red are very critical variables. We'll show it in the later presentation. So here's some analysis for the data. This density plot for children's BMI and also the parents' BMI. You can see the children's BMI is getting larger and larger over time, but the parents' BMI keep unchanged, especially the BM2, which is usually the father's BMI. And here's a scatter plot for between BMI and the parents' BMI. There are slightly positive correlation between them. This is a scatter plot between socioeconomic status and BMI. So there are negative correlation between them. We're going to use Bayesian network to build these models to investigate the correlation between all these variables. So Bayesian network is defined by a graph structure and also a set of parameters attached to this graph structure. Here's a toy example of Bayesian network with just 4 nodes. So the joint probability of these 4 variables can be decomposed into several conditional distributions given the graph structure. So this is the beauty of the Bayesian network. So it makes it simple. But learning a Bayesian network is quite challenging because the parameter space is quite large. So even when you are only modeling 25 nodes, there are order of 2 of power 300 possible DAGs. That's quite a huge number. And the parameter space is also discrete, so it poses further challenge for this learning job. So here are some existing algorithms for this learning Bayesian network structure. We're going to use the MCMC algorithms, specifically partition MCMC, to obtain a certain level of the structures. This graph is the result of VIV2 in B cohort. The main findings is birth weight and parents' BMI are the main factors of children's BMI. Socioeconomic status is the center node of this graph. And ME1, which is the mother's education level, impacts socioeconomic directly. And this is the results for V5 in B cohort. So physical activity becomes the factor of children's BMI from age 8. We also did this analysis for boys and girls separately. So they are a little bit different. So for boys, the physical activity is the factor for BMI, but it's not for girls. So based on this current results, we can get this main takeaways. So the children's BMI is mainly affected by the parent's BMI and his birth weight. The physical activity is important after age 8. Socioeconomic status is the center of the whole graph. And the mother's education level is also causal factor for socioeconomic status. We're also doing some other works. It's ongoing. We're working on subgroup analysis, longitudinal analysis. We're working on more efficient algorithms to learn Bayesian network. Also, we have to work on hybrid Bayesian network because in many cases there are also continuous and discrete variables in Bayesian network. So that's my presentation today. Thank you.
Thank you, Andy. That's it's very interesting working on the directed acyclical graphs, as they're known, but very difficult because it's 2 to the 300 is a very large number. It's literally like finding the needle in the haystack, and attaching probabilities to all those 2 to the 300 is well, it's impossible. So, but we hope we attach them to the most important ones. What I'd like to do now is introduce Roman, who leads our research in health and social environments, to talk about his work that he's been doing, which spans a number of areas. Roman.
Thank you, Sally. I'll do my best to reduce this originally 20-minute talk to 10 minutes or less. So I'll quickly go through, I guess, 3 projects today. Sorry, demographics and crime. How can we understand domestic violence using data science? Looking at the demographics of people. How can we infer how effective were the lockout laws in Sydney? And what is the best way to do predictive policing to solve problems with the potential issues when using data science to make decisions for police. So I guess this first paper is about understanding domestic violence particularly, and how we can build Bayesian models that help understand and ultimately make informed decisions about how to reduce violence. So we use criminal sources, where, when, what type of crime. And we also use demographic information about the population living in certain areas. And we combine both sources of information in a regression model, a probabilistic Bayesian model, to achieve the 2 things that Sally mentioned at the beginning: prediction and inference, understand what are the factors that are driving this. So how do we build these models? Well, we use a map of Sydney. This very detailed map, we know exactly the geographical regions that we'll be looking at crimes. And by overlapping these geographical regions, particularly SA1s in this case, we can get the number of assaults, the number of robberies, number of motor vehicle thefts, and so on. And then for each one of these same regions, we have census data, basically a whole bunch of variables that, using domain expertise, we can inform our models and put priors on the presence of these variables in the model. So things like income, education, disadvantage score, and so on, how are they possibly need to be included in the model or not. Then we, put all this data together in a huge database that contains basically the spatial regions. So we also consider that regions that are close by in space have a similar behavior in terms of crime. We consider all the demographics, and we're trying to predict Y in this case. So we're using U and X to predict Y. Now, I'll skip through the definition of the model, but I guess the important thing here is there are 3 components, and we have a whole bunch of unknown parameters that we're trying to learn. And these parameters, we learn them using MCNC, same as we've covered before. I guess I will jump this as well, but there's basically the first row there on the bottom is achieving prediction, and the second one is inference. The important thing, though, is that we can predict what the levels of domestic violence assaults will be for different regions based on their characteristics. And we can also understand which ones are the important characteristics or more relevant ones that are creating a launchpad for criminal activity. So in the example of domestic violence on the left, you can see that the number of males separated in an area are not surprisingly related to domestic violence, the population density as well, which has to do a little bit more with the reporting rate rather than the actual level of violence, and unemployment as well. So let me go to the next slide, really, because I want to cover all the projects. This is very sort of innovative stuff that we're doing. This particular project on the lockout laws was looking at the dynamics of crime. So everyone of you is aware of the lockout laws were introduced in 2014 and had several problems, in terms of the way that everyone understood that they were being effective. They meant a 1:30 a.m. lockout at hotels, clubs, nightclubs, and so on, and 3 a.m. cessation of alcohol service. Now, we wanted to understand how is crime changing based on the introduction of these laws at different regions. So we looked at King's Cross, which is the red area in the slide. We looked at the CBD, the proximal displacement areas in green, and the distal displacement areas in yellow. We placed sort of like a complex statistical model that I'm not covering today, called AdaptSpec, and non-parametric regression as well over time. And we found that you can see the red curve on the bottom there, that is King's Cross. We see a sharp decrease in crime around 2014, which was expected. And I guess many people actually realized that there was a big change in King's Cross, but it was not the same in the CBD, which is the blue line on the top, where actually the bulk of the crime was happening. And you can see that non-domestic assaults were already coming down back in 2008. And after the introduction of the laws, that pace of decrease actually slowed down. So if anything, crime started going up after 2015. So what we did was essentially try to bring our research and help decisions that are being taken based on data. So we submitted a report to the parliamentary committee on the study of the lockout laws and the impact of the lockout laws on the late night economy. And I guess we were very happy with being able to communicate our results, and particularly how we communicate and use uncertainty to make decisions as well. So this model that you see here on the left is the predictions of crime starting in 2014 with the introduction of the laws. This is a very simplistic models that people from the Bureau of Crime Statistics and Research were doing, but they were not considering uncertainty. So they were concluding that crime was coming down in the CBD, but when we started taking into account this uncertainty, there was not really a 4% reduction, as you see on the plot on the right, but actually there's a big variation of the possible percentage decrease of crimes, which goes anywhere from -15 to +5 in this case. So last but not least, I guess, is predictive policing, which is trying to use the dynamics of crime as well to decide where should police go next. And it has some ethical issues, but we'll go quickly try to cover through that. So very, briefly summarizing what is that we do. There's a map with we divide into quadrants and into sort of like a grid with all the crimes. Each one of these crimes, basically, we assume follows a Poisson distribution, which is a positive distribution that has an intensity function that we want to model. This intensity function, we again model as a Gaussian process, but all this is, I guess, trying to fuse the information coming from all the data sources, so each one of the crimes at all these different regions, and we combine that to do Bayesian analysis to estimate the inference, which is basically what are the parameters of our Gaussian process over space and time. This allows us to do two things: predict when the next crime is going to happen potentially, and what is our uncertainty around those values, and then we use that to make decisions, right? So this toy example here shows a police car moving following one route, following one path, evaluating what the reward is, should it explore, should it exploit its knowledge. And we conduct this decision tree, decision-making sort of algorithm that evaluates hundreds and even thousands of different routes. And ultimately, you pick the one that gives you the highest reward, that is balancing exploration and exploitation. This video here shows this algorithm in actually working in simulation with real crime data. The police car that you see there, on the top is the ground truth, right? The known locations where crime is happening. And on the bottom is the car exploring the environment. And as you see, it's making online decisions in terms of going to areas where it's uncertain about what the crime level sees, and at the same time going to areas where there's higher amount of crimes in that particular region. So it will keep visiting areas that are potentially more prone to crime, but at the same time explore. And I guess that's where most of the ethical concerns are, because people are actually discussing, this is across the world, particularly in the US, where this is actively being used by police forces, is that police will be over-policing, going to systematically policing certain areas more than others. But importantly, what our methods allows is to actually control that level of exploration and exploitation with this so-called, in this case, a kappa parameter, which is an acquisition function in our algorithm that allows us to control how much you are revisiting existing location and exploring others. So I guess that's the talk for today. Let's just jump into questions if there's still time. Thanks.
Thank you. Well, I hope that you get a good sense of this type of work that we're doing. It's a lot of fun. Some of it is quite complicated maths, but it's actually all applying it to areas that probably have not had these sorts of maths applied to them before. And we feel very lucky to be able to do that. All right. Thank you, everybody.